Hello. In this lecture, we are going to deal with inductance, its property, how it is going to work in DC supply and AC supply. Welcome to the lecture. Inductance is represented by the symbol L. It is measured in Henry. Henry is the unit of inductance. The notation is H. And we will be seeing when I connect a DC supply, what happens. When I go into supply the AC supply, what is going to happen. When I connect a DC supply, inductance is going to get short circuit. DC I use capital notation. DC voltage is V capital V, DC current is I. For inductor is connected to DC, inductor is short circuit. Let us see why this is happening. First thing, for an AC source, when an AC circuit, the inductor is represented by the L and the voltage across the inductor is V of t into I of t. And remember, the voltage across the inductor is given as V of t equal to L into di of t by dt. This is always true by only for the passive sign convention. What is passive sign convention? The current will be entering the positive of the voltage. For this convention only, this is true. Suppose if I say this current is I1, now the relation will become like V of t equal to minus L d I1 of t dt. Keep in mind, right? Here, why I have put minus sign? Because I1 is entering the minus part of the voltage, right? So I will represent by minus sign. So whenever I say V equal to L di by dt, the meaning is I is entering the plus of the voltage. This convention is called passive sign convention. This I have explained in the part 1 of the lecture, right? Basics of electric networks. I have posted in the same channel, Fundamentals Learners. You can observe, you can watch those videos, right? Okay. So if I say V equal to di by dt, the meaning is the expression is positive only for passive sign convention, right? Now, what about I? Okay, what about I? Take L to the left side, it becomes 1 by L. Then dt to the left side. So I need I, so I integrate on both sides. I will be getting like I of t equal to 1 by L integral of Vt dt. It should be like Vt dt. Okay. And what about this? What is this? I naught. I naught is the initial current. I naught is the initial current, because inductor can hold the current value or store the current value. Look, whenever I integrate, I use a constant called integration constant in mathematics, right? What is the meaning of that is, see, I am integrating from 0 to time t. So before 0, the inductor may hold some current. That is why I mark this as I of 0. Normally we will take initial current as 0. Suppose initial current is given, that is at I naught, the current is 1 milliampere, means here I will put 1 milliampere. Okay, so look the lower limit of the integration. It is 0 to t, this initial current is I of 0. If it is from 2 to t, the initial current is I of 2, current at time 2. So understand the relation clearly between voltage and current of an inductor. Okay, and current and voltage between an inductor, and what is an initial current. Now based on this expression, you can observe that, see, when I is constant, for a DC supply, this I is going to be constant. When I differentiate a constant, okay, constant is not changing, so differentiation is rate of change. So this term becomes 0, right? When this term becomes 0, V of t becomes 0. That is why when I is constant, that is DC, voltage is 0. Voltage is 0 means short circuit. That is what we marked here. When I is constant, voltage is 0, represented by the short circuit. This is the first inference from this expression. Second inference, when the sudden change in I of t is suddenly changing. What is the meaning? Let me say this is my I of t. Okay. I of t is suddenly changing. This is the sudden change, right? Okay, darker side. This is the sudden change. Sudden change means What about the change in I? let me say this is 0, this is 2 ampere, right? The time is 3 seconds, right? What is di by dt? What is di? The change is from, what is the terminating value? Ending value 2, starting value 0. So di is 2 minus 0. Okay. What is dt? Change in time. Change in time is, that is at the same time 3. So change in time is 3 minus 3. So what is di by dt? Di by dt is 2 divided by 0, which is infinite. Okay, which is not practically possible. For a sudden change in I of t, di by dt is equal to infinite, thereby v is equal to infinite. We will be tending to infinite, which is not practically possible. So what we are going to infer is sudden change in I of t is not permitted or not practically possible. It's not practically possible. Okay, so two observations we make. For a DC, inductor is short circuit, that is the voltage is 0. Then inductor resists sudden change in current. Fine. Okay. Now we will observe a series inductance circuit, right? Inductance where some inductors are connected in series whose inductance are L1, L2 and L3. So we know I apply Kirchhoff voltage law for this loop. The current is I of t. The current is I of t, and okay, I'm going to write this voltage is V. This voltage, source voltage, is equal to sum of all voltages. This voltage is L1 di1 di by dt. Since all current are same, I can say they are in series. Okay, so it is L1 di by dt, L2 di by dt plus L3 di by dt. So I take di by dt outside, it becomes L1 plus L2 plus L3. Okay, so these all resistance can be said as an equivalent resistance, L equivalent. So instead of saying L1, L2 plus L3, I can replace this as L equivalent. Okay, so this is thing when the inductors are in series, I can add their inductance values L1, L2 and L3. Now come to the parallel, when the inductors are connected in parallel, what happens? How I say this in parallel? Because all the elements are connected to the same pair of nodes, right? L1 is connected to this node, L2 are connected to this node, L3 is connected to this node. Other end of the elements is connected to this node, right? So they are in parallel. In parallel, voltage is the same. Okay, I will mark the nodes as this. Okay, this is a node. This is another node, right? All elements are connected to a common node. So the voltage is the same. What is the voltage at the node? This is V, this is ground. Okay, so the voltage across each element is V. So I can apply Kirchhoff current law. I can apply Kirchhoff current law KCL to the node. And what is our conclusion? If this incoming current is I1, outgoing incoming current is equal to outgoing current. That is your Kirchhoff's current law. So I of t is equal to I1 of t plus I2 of t plus I3 of t. What is I1 of t? Current through the inductor, right? L1. I2 is current through the inductor L2. I3 is current through the inductor L3. Okay. So 1 by L1 integral of V of t dt plus 1 by L2 integral of, because voltage is the same. So for all currents, the voltage will be the same. But the inductance value will be 1 by L1, 1 by L2, 1 by L3. Here I am taking integral of V of t dt outside. It becomes 1 by L1 plus 1 by L2 plus 1 by L3. That is equal to 1 by L equivalent. So 1 by L equivalent is nothing but 1 by L1 plus 1 by L2 plus 1 by L3. These two results are very similar to the resistance, right? In resistance also we add when they are in series we add, when they are in parallel we will make this 1 by R equivalent equal to 1 by R1 plus 1 by R2, 1 by R3. They same procedure, right? Okay. Now when they are in L resistance or in L inductance or in series, means what I can do? I will add everything. If they are in parallel, I will do this operation. Okay, right? And if two inductance are in parallel, it becomes 1 by L equivalent equal to 1 by L1 plus 1 by L2 and if I these manipulations, finally L equal to L1 into L2 divided by L1 plus L2. This is applicable only for two inductors are in parallel, right? The same I have explained in resistance also. You can watch that video. When three inductors are in parallel, I cannot say L equivalent equal to L1 into L2 into L3 divided by L1 plus L2 plus L3. This is wrong. You should not use this, right? Okay, most people will try to solve this way. It's wrong. It is this multiplication of the resistance inductance value divided by the sum of those values is applicable only for two inductors are in parallel. So which is the best way to go is solve these two inductance, get a value. They are in parallel, and with that value solve with L3. Like that we can go, or else you solve 1 by L equal to 1 by L1 plus 1 by L2 plus 1 by L3. This is also another way to solve. Okay, this is a very important information. You cannot extend this idea for more than two inductance. Okay, right? That is what I have said here. When they are in three are in parallel, I cannot apply this rule. Okay, for three, this is the way to go, right? And in the what is in C, if they are in L inductance are in parallel, some inductance are in parallel means L equivalent will be definitely greater than the largest value. If they are in series means, okay, L inductors are in series means L equivalent is greater than the greater than the largest value of the inductor. If they are in parallel means L equivalent will be smaller than the smallest one. Okay. Now n inductors, n number of inductors are in series, so equivalent will be n into L. Now n inductance of L are in parallel, so L equivalent equal to L by n. Now we work out few problems. Okay, observe the circuit. They are asking to find the equivalent. They are asking to find the equivalent L values, right? Observe what are the inductors are in series and in parallel. If you observe very closely, these two are in series, right? They will carry the same current. So 2 and 2, this can be solved as 4. Okay, so I can mark this as this 2 and 2 gives 4 Henry. This 4 Henry and this another 4 Henry are in parallel, right? So this is the 4 Henry. They are in parallel. When they are in parallel, what we do? We will multiply those values and we will add those values and we divide. Right. So 16 by 8, it is 2 Henry. So this I will mark you some other color. Okay. Now this entire red becomes 2 Henry. Okay. Now the result is in series with 3 Henry. Okay, this entire setup which I marked in red circle is in series with 3 Henry. So 2 plus 3 it becomes 5. I will use some black color. Okay, this becomes 5. This is your 5 Henry. So this 5 Henry is in parallel with this 5 Henry is in parallel with this 5 Henry. So 5 parallel with 5, the result is 5 into 5 divided by 5 plus 5. So 25 by 10 is equal to 2.5 Henry. Okay. So this 2.5 Henry, is in series with 5 as well as in series with 2. The circuit will be now, I can draw it here, 2 Henry, 2.5 Henry and 5 Henry. Okay, what I have done is this entire thing I have simplified it to 2.5. I marked 2.5. Already 2 Henry is there. This is 2 Henry. This is the 5 Henry. It's already there in the circuit, right? This is 2 Henry. This 5 Henry is there. This entire thing is simplified to 2.5. Now you can add everything. 2 plus 2.5 plus 5. So the final answer is 9.5 Henry. So this is the final answer, L equivalent. Okay, so L equivalent for the circuit is 9.5 Henry. Okay. Now you look at this problem, the second problem. In this, a voltage source is given. They are asking what is the current, right? What is the voltage value given? The voltage value given is 6 sin omega t, right? They are asking current. We know what is the relation between the voltage and current. So current is 1 by L integral of V of t dt plus initial current. Since we are going to integrate from 0 to t, initial current I put as I as 0, right? So initial current is not given, so I take this term as 0. Just an integration. Sin omega t integrate with respect to dt, so it is minus cos omega t by omega. Now we substitute the limits, so this is the final answer, right? Okay, right. Now let's look out this problem. This is a very interesting problem, right? Okay, in this circuit, I is given, inductor value is given. Okay, now the question is, they are asking to draw the value of V of t. They have given the waveform of I of t. The question is, draw the waveform of voltage V of t, right? So what is V of t? V of t equal to L di by dt. If you look at this current waveform, L is 2 Henry, no problem for us. What is di by dt? Di by dt is this waveform. Okay, so what are the, see, its waveform is not a uniform shape, right? Between 0 to 1 it is a rising slope, between 1 to 2 it is a falling slope, up to 2 it is suddenly increasing, between 2 and 3 it is constant, at 3 is suddenly falling. So we have to work at each segment separately. So between the time 0 and 1, between the time 0 and 1, right? What is di? Di is change in current, right? Between the time 0 and 1, what is the change in current? 2 minus 0. This is the change in current, 2 minus 0. What is the change in time? 1 minus 0. So V of t equal to L into di by dt. L is 2, di is 2 minus 0 is 2 by 1, dt is 1, so it is 4 volt. Okay, so between 0 and 1 it is 4 volt. Okay, next, between 1 and 2, between time 1 and 2, what is happening? What is di? Di is where it is ending? 0. Where is the starting point? Ending point minus starting point, that is your di, right? I am working between 1 and 2, right? Where it is ending? I is ending at 0. Where it is starting? 2. So 0 minus 2. What is the change in time? Ending time is 2, starting time is 1, 2 minus 1. So V of t is equal to L is 2, di by dt is minus 2 by 1, so it is minus 4. So between 1 and 2 it is minus 4. Okay, next, at 2. At 2 what is happening? di. What is di? Change in current. Okay, where it is ending 2, where it is starting 0, so 2 minus 0. What is dt? Change in time. During this time it is 2 minus 2. So di by dt is 2 by 0. So anything by 0 is infinite. I will represent by the impulse symbol. Impulse symbol. Okay, now between 2 and 3. 2 and 3. Between 2 and 3 it is a constant, right? So di is constant. At 3 it is 2, at 2 it is also 2. So 2 minus 2 it is 0. di is 0. What is dt? Change in time. Between time 3 minus 2 it is 1. So V of t equal to L di by dt. L is 2, di is 0 by 1. The answer is 0. So between 2 and 3 voltage is 0. Okay, now come to the time 3. Come to the time 3 means what is happening? The voltage is at 2, it is coming to 0. So what is di? 0 minus 2. So it is minus 2. What is the change in time? It is the same time, 3 minus 3, it is 0. So 2 into minus 2 by 0, it is minus infinite. Okay, so this is the waveform. Remember, when it is going to infinite, we will use the impulse symbol. Impulse, we put a cap. Okay, right. One more problem. Okay, in this problem they have given a V wave voltage waveform. They are asking what is the current waveform, right? And you know the current voltage, the relation between the current and voltage. Voltage is given, I have to find the current, right? So 1 by L 0 to t V of t dt and plus initial current. Okay, now we can see it is of some segment. 0 to 1 it is 2, 1 to 3 it is minus 2, between 3 to 4 it is 2. This is how the waveform is, right? Voltage waveform. So I take each segment between 0 to 1. L is 2, I limit is 0 to 2 dt, because between the time 0 to 1, what is the voltage? It is constant 2 dt plus initial current. Initial current, that is at I equal to 0, it is not given, so I take this as 0. Okay, so 2 will take outside, 2 gets cancelled, 0 to t dt. So I substitute the upper limit, it becomes t, right? So the waveform between 0 to 1 is t. Okay, so how can I draw the waveform t? I can put the values like at 0 t equal to 0, I of t equal to t. Okay, I of t is equal to t. At 0, I of t equal to 0. At time 1, I of t equal to 1. At time 0.5, I of 0.5 equal to 0.5. Okay, so this is the line, right? At 0 it is 0, at 1 it is 1, at t equal to 0.5 it is 0.5. So this is the waveform of t. Okay, now we come to the next segment between 1 and 3. Between 1 and 3, what is the value of V? It is minus 2. Minus 2. What is the initial current? I am working from 1 to time t, right? So what is the current at 1? If I put between 0 to 1 is this. At current, if I put 1, the answer is 1, right? So the initial current, when I going to work in this segment, now the initial current for this segment is 1. Okay, now you substitute the limits 1 to t, upper limit is t minus 1, and solving I get minus t plus 2. This expression minus t plus 2 is valid between the time interval 1 to 3. Now you substitute 1, what you get? Minus 1 plus 2. At time 1, the value is 1. At time 1, the value is 1. Okay, now you put time equal to 2, minus 2 plus 2, it becomes 0. At time 2, the current becomes 0. Now you put time equal to 3, minus 3 plus 2, it becomes, at 3 it comes to minus 1. So I can draw a line, I can connect those points, right? So this is the shape of the waveform, minus t plus 2 when the time is between 1 and 3. Now we go between the time segment 3 and 4. Between 3 and 4, what is the amplitude value? 2. So I will integrate from 3 to t. At 3, what is the current? I can use this. At 3 means I can use the previous segment final value, last value, that is the initial value for this segment, right? The final value of this segment is the initial value of this segment, right? So if I put t equal to 3, I get minus 3 plus 2 minus 1. So I of 3 is minus 1. Now substitute the limits from 3 to t, I get this t minus 4. So for this segment between 3 and 4, the equation is t minus 4. Now you put the values of t. 3 if I put, I get minus 1. If I put 4, I get time as 4, I get 0. So if I connect the point, I get this, right? So this is how the waveform of I of t will be. Given V of t is this waveform. Okay. And use our common sense, integration is nothing but adding or finding the area, right? For a positive constant, it will be a rising slope. So for a positive constant, it will be a rising slope. For a negative constant, it will be a falling slope. Similarly, a positive is coming, so the slope is rising. So whenever, for what time it is a positive, the slope is rising. For a negative, the slope is falling. When it is negative, between 1 and 3 it is negative, we can see it is a falling slope or a negative slope. Between 3 and 4 it is positive, we can see the slope is rising, positive slope. Between 0 and 1 it is positive, it is a rising slope. This is some common sense observation, right? Okay. But we have to know how to solve when the initial condition will be, that is very important, right? Okay, hope you enjoy this lecture. Thanks for listening. Do subscribe the channel. Happy learning.